The next section we're going to look at is a section on area and the definite interval. What we're going to have in this section is we're going to have a graph. For example, this one. Here we have y equals minus x squared plus 5 between 0 and 2. And what we'd like to do is we'd like to find the area under the curve. Now, the problem with this curve is just that it is a curve and it's not a straight line. If we had a rectangle or a triangle, it'd be fairly straightforward to find the area. But for a shape like this, or even something more curved, it would be very difficult. So what we're going to do is we're going to chop this area in here, because we'd like to know what this area is. We're going to chop it into some shapes that we can calculate the area of. And that shape is going to be a rectangle. So what I'm going to do is I'm going to chop it into any number of rectangles I want. And the rectangle has some width. And the rectangle has some height. And the area of the rectangle is going to be width times height. So what we're going to do is we're going to chop up this area into a number of rectangles. Now, for this first example, I'm going to chop it up into 5 rectangles. And so what we do is we want to chop it up into 5 rectangles. We have to know how big those rectangles are. Now, our interval goes from 0 to 2. So generally what I would do is I would draw a number line, just a line, with my start and end points on it. Then you want, in this case, we want 5 equal subintervals. And so if we break this up into 5 pieces, 1, and 2, 3, 4, 5. 1, 2, 3, 4, 5 pieces. If we break it up into 5 pieces, each one is going to be the same length. And it turns out that that length, or width, I should say, is 2/5. Because I took a length of 2, from 0 to 2 was size 2, and I chopped it up into 5 pieces. So each piece is of width 2/5, which is the same as 0.4. Then I have to know, where does each of these pieces end up? Well, if I start at 0 and I add 0.4 to it, I get to 0.4. And then I add 0.4 again and I get 0.8. And I add 0.4 again and I get 1.2. And I add 0.4 again and I get 1.6. And I add 4 again and I get 2.0, which we could put there if we wanted to. Now, when I divide my shape into rectangles, and I'm going to go back one screen here for a moment, my rectangle is going to fit, let's say, inside my curve. And so the width of the rectangle, I've chopped it up into 5 pieces, so this is here 0.4. And the height is going to be the function value, because it comes right up to the curve. So the height here is the function value at 0.4. Or if you like fractions, the function value at 2/5. So what I need to do is, if I'm going to chop this up into a bunch of pieces, I need to know the height of each of the pieces. And each of those heights is going to be a function value. And in fact, it's going to be a function value at each of these points, 0.4, 0.8, 1.2, 1.6, and 2. And so what I'm going to do is I'm going to calculate all of those numbers. These numbers in this table, these are the heights of the rectangles. Now, my next slide, I have the curve with all 5 rectangles. And what I'm going to do is I'm going to label these heights, because this x value is 0.4, and then we have 0.8, 1.2, 1.6, and so from my table, this height here is 4.84. This next height was 4.36. The next height, 3.56. The next height, 2.44. And the next height, 1. So if you want to find the area of the very first rectangle, I'll call that area 1. It's the height. Well, let's write it this way. Width times height. So area 1 is going to be width, which is 0.4, times the height, which is 4.84. And I'm going to keep doing that. This one here is going to be area 2, and area 3, and area 4, and area 5. All of those areas are calculated the same way. The width, which is always going to be 0.4, and the height, which is going to be the function value right there. And so the width, which is 0.4, and the height is the function value. And then I can add them all up. I take area 1 plus area 2 plus area 3 plus area 4 plus area 5. Now, you'll notice that when I do this, I get a little bit of error on each of these. So there's a little bit of space in here which is not accounted for, and a little bit of space in here which is not accounted for. And this red part is the error. So when I do these rectangles this way, my estimate is going to be a little bit low to the true area. But what we can do, that's what this slide says. It talks about the fact that each one of those is low. So what we do is we add them up. Now this notation up here, r sub 5 is equal to, this is the Greek symbol sigma. It means add them up. And what are we adding up? We're adding up 5 from 1 to 5. We're adding up 5 pieces. This f of xi, that's the height. And this delta x, that's the width. So if we come back to our picture, whoops, delta x, that's the width of any one of our rectangles. And it's always 0.4 for these guys. Or 2/5. So this is f of 2, for example, that's the height. 2/5, that's the width. And the same thing, height times width. Height times width. Height times width, and so on. And so you add up all those areas, and the rest of this is just a little bit of algebra. Um, and because I had the same width for each one of these rectangles, I could pull that out front, factor out the 2/5. Whoops. Factor out the 2/5, and then you don't have to multiply it every time. You add up all the heights, you multiply by 2/5, and you get an estimate 6.48. And as we said, that estimate is low. Now, we could do essentially the same thing, but instead of taking the right-hand endpoint of these rectangles, we could take the left-hand endpoint. And then my heights are bigger, at least for the first one. And I stop, well, I start at 0 this time, and then I go to 0.4 and 0.8 and 1.2 and 1.6, and those are my heights. And now, when I calculate this, I'm going to have a little bit of extra area. This is going to be an overestimate. And it's going to be over by these little or big triangles in red. But it's going to be basically the same thing. Area 1 plus area 2 plus area 3 plus area 4 plus area 5. And each one of those areas is height times width. The width is still 0.4 or delta x. And I'll just say that's the width. And the height is the function value. And we just take our function values off the table. And here, the reason it says L sub 5 is because I used left endpoints. The other one was R sub 5 because I used right endpoints. But this is still the same story. This is height times width. And you don't have to worry about the symbols in the equation. You just have to know that its height is the function value, and width is always, for these, 2/5, because that's my delta x. And because I have a 2/5 in each of these terms, I factor that out, I add up all the heights, and I get 8.08. And that's an overestimate. That's a little bit big. And so the true area is somewhere in between there, between 6.48 and 8.08. Now, both of those were either entirely over or entirely under. But there was no magic to picking the left endpoint or the right endpoint. I could have picked any point inside that interval and essentially accomplished the same thing. So if I pick midpoints, I'm going to get an even better estimate, because on each of these rectangles I get a little bit under and a little bit over, and a little bit under and a little bit over, a little bit under and a little bit over, and a little bit under and a little bit over. And these errors, while they don't cancel each other out exactly, they do cancel each other out somewhat. And so this is going to be a much better estimate than either the left or the right. The trick here is finding the midpoint. So if my endpoint is 0.4, then the midpoint is halfway between 0 and 0.4, which is 0.2. Now, the width of each of these intervals is going to be the same. So if I go to the midpoint, I find here 0.6, and this is delta x is still 0.4. And then you come here to 1, and then 1.4, and then 1.8. So area 1 plus area 2 plus area 3 plus area 4 plus area 5. The only trick here too is finding the height, which is going to be right there. That height is going to be f of 0.2. And this height here is going to be f of my x value down here, 0.6, and so on. F of 1, f of 1.4, and f of 1.8. And this one's called M5 because I did the midpoint with 5 rectangles. But it's still the same story. It's the height times the width. And the width is still the same in each of them, and so you can factor that out. And we get that 2/5 out front. You add up all the heights, multiply by 2/5, and it turns out the 7.36 is actually a fairly reasonable estimate for the area under the curve. Now, you'll notice that even on the midpoint formula here, we have some fairly large rectangles. Triangles, I mean, for the error. That's a pretty big error right there. So if you want to improve your estimate, what you do is you simply take more rectangles. Here, whoops. Here, for example, we're taking 20 rectangles. And you can see there that my errors are actually very, very, very small. And even down here at the end, I don't get much error. I get some pretty small errors. And they do have a tendency to cancel themselves out much nicer when you have 20 rectangles instead of 5. All of these rectangle methods of estimating the area are just that. They are estimates. They are not going to be exact. Now, if we want an exact answer, what we do is we take an infinite number of rectangles. So for an exact answer, you need infinite rectangles. And how can we do infinite rectangles? Because if I take an infinite number of rectangles, each of them is going to be of size 0. And I'm going to be adding all day. So I don't actually chop it up into an infinite number of rectangles. What I do is I do this thing known as a limit, which we saw earlier. And in this particular case, my limit is infinite rectangles, because here n is the number of rectangles. N equals number of rectangles. Now, we're never going to take this limit. The only thing we're going to mention about it is that when I take an infinite number of rectangles, I find the exact value of the area, and I call that the definite integral, the area under the curve. And I represent it by the integral symbol, and I put numbers on it, a being the lower limit and b being the upper limit. These are numbers. A and b are numbers. So we're going to look at these, how to solve something like this with an integral in the next section. But for now, it's enough to know that if you do an infinite number of rectangles, you can solve that using an integral. In this section, though, we are going to be using just rectangles. Now, this example is, well, pretty similar to the previous one, because now it's x squared. And what I'm going to do is I'm going to graph this just so we get an idea of what it looks like. It is a parabola. And it goes from 2 to 4. So we're going to find this area here. This height is 4, and this height is 16. This is not the scale. And so if we do 2 subintervals, we're going to get a fairly poor estimate. So I'm not even going to do that one. I'm actually just going to do 5 subintervals. And it says compute the Riemann sum, but I didn't tell you whether or not to use left endpoints, right endpoints, or midpoints, so we're going to do all 3. So the first thing we're going to do is, if we're going to do 5 intervals from 2 to 4, what I'm going to do is I'm going to figure out what those intervals, what are the x values for those intervals. From 2 to 4. We're going to chop it up into 5 pieces. 1, 2, 3, 4, 5. Now, how big is each piece? What's my delta x here? Well, the length of the interval is the right side minus the left side. So it's 4 minus 2. And I'm going to divide that into 5 pieces. And so that's the size of my delta x, or the width of each of my rectangles. And let's see, that's 2/5, just like in the previous problem. And so what we want to do here is we want to take and we want to figure out what are all my x values. So we have 2, we have, let's see, this is 0.4. It's probably going to be easier to work with 0.4. So we have 2.4, 2.8, 3.2, 3.6, and 4.0. So those are the x values. Now if we use the right-hand endpoints, we would use, we'd start at 2.4 and we'd go up to 4. And if we use the left-hand endpoints, we start at 2, because that's on the left, and we go up to 3.6. No matter which side you start at, you're only going to do 5 heights. So you either get the first one or you get the last one, but you can't get both endpoints. And if you do midpoints, you don't get either of the endpoints. So we have 2, 2.4, 2.8, 3.2, and 3.6. So let's do our right-hand endpoints. So for the right-hand endpoints, and I'm going to call it r sub 5 because there are 5 of them, I'm going to add up. No, we're not even going to do that. We won't use the notation. We'll just add them up. So I'll just say this. Add up height times width. Height That's going to be f of x, and the width, that's going to be delta x. So our first one is going to be f of 2.4 times 0.4 plus f of 2.8 times 0.4 plus f of 3.2 times 0.4 plus f of 3.6 times 0.4 plus f of 4 times, and I'm going to write here 2/5 because I'm out of space, times 2/5. And don't forget your function is x squared. So I'm going to factor out the 0.4. And so you get 2.4 squared plus 2.8 squared plus 3.2 squared plus 3.6 squared plus 4 squared. If you add all those up, we add them up here. So 2.4 squared is 5.76. And then 7.84. And then 10.24, and 12.96, 4 squared, I can do that one, that's 16. And so you add them up, multiply by 0.4, and you get 20.976. Now, the question becomes, is that an overestimate or an underestimate? Well, you can look at your graph to determine that. So if we look at our graph, I'm just going to sketch it down here. If I make a rectangle, 2 to 4, my first rectangle, if I take a right-hand endpoint, is going to come up here, it's going to come over, and it's going to be an overestimate. And in fact, each of these is going to be an overestimate. So this number that I calculated here, 20.976, is an overestimate. And we can tell that just from looking at the graph, because we took right-hand endpoints. So if we take left-hand endpoints, we're going to get an underestimate. And when I do the left-hand endpoints, I'm going to get something very similar. We're going to take. But now, let me go back here for a second. We're going to start at 2 for for the left-hand endpoints, because that one's the very first one we get to on the left. So now it's going to be f of 2 times 0.4 plus f of 2.4 times 0.4 plus f of 2.8 times 0.4 plus f of 3.2 times 0.4, I run out of space again, plus f of 3.6 times 0.4. We're going to factor out the 0.4 again, and I know what those numbers are. F of 2 is 2 squared, which is 4, and I can take my other numbers from my previous problem, 5.76, 7.84, 10.24, and 12.96. So now we add all those up. And we get 16.176. And that's, of course, an underestimate. So you can see that my first number was 21 or so. This one's 16 or so. And so if I do midpoints, I'm going to end up in the middle. But now for my midpoints, I have to recalculate. Because now we're going from 2 to 4. Let's see, 2.4 here. But the midpoint is going to be 2.2. And the midpoint of the next one is going to be 2.6. The midpoint of the next one is going to be 3.0. And the midpoint of the next one, I'm going to draw big lines for my actual divisions and little lines for my midpoints. 3.4 and 3.6. But it's the same story. I'm going to call this m sub 5, and I'm going to factor out my delta x to begin with. So it's going to be 0.4 times. Now I use my midpoints, 2.2, 2.6, 3.0, 3.4, and 3.6. F of 2.2, f of 2.6, f of 3.0, f of 3.4, and f of 3.6. If you're wondering if you've added too much or not enough, you can just count them up and you should have exactly 5 pieces. 1, 2, 3, 4, 5. And so let me add all those up. That's 45.12. Multiplied by the 0.4, you get 18.048, which is roughly exactly halfway between the other two estimates. But all of the problems essentially work the same way. You find your interval, you chop it up into the appropriate number of pieces, you find the x values that you want, you find the heights. Each one of these function values, these are all height. And the 0.4, that's your width. And you're just adding up rectangles. Height times width plus height times width plus height times width. And then you get your estimate. That concludes this section.